Our next speaker is Gabriel Scherer on again on GADTs, but this time combining GADTs with subtyping.
Actually, it's not really subtyping because subtyping gets a bad press. It's variance, which is related but not exactly the same thing. So this is work which I did at Delion with advisor Didier Remy. And it doesn't work. It worked just 1 hour ago, but okay, so you've seen the presentation of GADT, so I can go a bit fast on this. GADTs is basically algebraic data types plus type equalities, plus existential types, but I don't care about that much. So, for example, the simply typed, the algebraic data type that with two constructors int and bool for integers and boolean could be translated as a GADT into, on the left you see an imaginary syntax that exhibits the equalities. So I'm saying, I know I add an alpha type parameter and I say, okay, it's the same constructor but with the equality alpha equals int, and in the second case alpha equals bool, or the concrete syntax that we use on the right with the equation implicit in the return type. And I can write a pattern matching similar to the example of Jack's evaluation function. If it was my simple X type here, that wouldn't type check because the two branches have different types. But thanks to the local equalities I add when I pattern match on a GADT, well, both have the return type alpha. Variance on the other side is a notion that is traditionally linked to subtyping, which is motivated by subtyping. So subtyping, I suppose you are familiar with that. Sigma is a subtype of tau. If all values of type sigma are also values of type tau. I have the usual subtyping rule on arrows with the contravariance on the left, the reverse direction of the relation. And if I have parameterized types, being simple types or GADT or whatever, I'm interested in knowing how variance, how the outer type depends on the parameters type. So in this example, I have a type T with three parameters, one contravariant, one invariant, and one covariant. And therefore, when I check the subtyping relation for T, I check the corresponding relation, inverse or equality, for the parameters. The question is, if I'm given a variance annotation like this one, how do I check that this annotation is correct? So for simple types like here, it's easy to check. There is a discipline of if a variable appears in a negative position, then it's covariant, contravariant. If it appears in a positive position, it's covariant, and if it appears both in a negative and positive position, it's invariant. But for GADTs, well, it's actually harder than it seems. How do you extend this check? So this type, for example, which will be my running example, has two constructors, val, which is actually a regular algebraic constructor, and prod, which takes two existences type, beta and gamma, takes an expression of type beta and an expression of type gamma, and returns a beta times gamma s. I claim that this type is covariant plus alpha. Is it right? Is it wrong? Well, so who knows? I think this one is right. So actually, I wrote an example like that, and I was surprised that the Ocampo type checker completely said, no, this is wrong. Alpha is invariant, and it annoyed me for what I was working. And then I said, okay, there must be a simple criterion. I sent a message on my list. See, we could try that, for example. And Jack answered with an example like this one. So this one uses private types, which is a feature of the Ocampo type system, which allows to make semi-abstract definitions. The idea that if I say a file descriptor is a private integer, I mean that a file descriptor are subtypes of integer. If I have a file descriptor, I can see the underlying integer, but if I have an integer, I am not allowed to forge an arbitrary file descriptor. So I can say, I have a library that makes this definition and provides me with a few file descriptor or function to create file descriptor, such as standard input. And then I create a GADT T, which takes, we have a file constructor which takes a file descriptor as a parameter and say that the alpha is then equal to file descriptor. Is this data type covariant? So if it's covariant, let's say it is, well, I can define a value of that type, file of std, and I can coerce this value. In OCaml we have a bit of subtyping, but it's all explicit, so we are not too ashamed of it. So I can coerce this value to an int t, because filedest is a subtype of int, therefore filedest t is a subtype of int t is covariant, into a value O prime of that int. But then things go wrong, because in fact what I do in this example is I can use, oh, this is even not possible. I can use the equality that I have to this branch of the pattern matching, and then this function of type filedest to filedest, I can implicitly type it at type alpha to filedest for alpha t, the variable of my GADT. And therefore, if I give to this function an int t, I get out an int to filedest function, which allows me to forge arbitrary file descriptor from integers, meaning I broke the soundness property of my private data types. I can have the example that crash the machine, but this one is already unsound. So why is this one unsound? But I claim that the first one is correct. Well, the one way to check that this is correct is, well, I could almost write the casting function myself. So let's try to do that in a pseudo code with, imagine we had coercion types. Well, I say, if you tell me that alpha is smaller than alpha prime, I can write a coercion from alpha x to alpha prime x. How do I do that? Well, if I have a value, it's easy. A value at type alpha, I coerce it to alpha prime, you get an alpha prime x. And if I have a product type, so I have beta, gamma as type variables, and I have two parameters of the right type, well, I know that alpha is equal to beta times gamma. This is my local equation. And I know that alpha is smaller than alpha prime. Well, what I should do is apply the prod constructor, but to get something of type alpha prime x. But to apply the prod constructor, I must get a product out. So is alpha prime a product? Well, so the answer as a meta theorem about the OCaml type system, I hope it's true, is that if something alpha prime is bigger than a product, if beta times gamma is smaller than alpha prime, then alpha prime is itself a product. So alpha prime is of the form beta prime times gamma prime with the obvious subtyping relations due to the covariance of the product. So let's say I have these new types in the hand, and I can write prod beta times gamma prime, cast the things, and it all works, more or less. So what I use here is a condition of upward closure. I said for a type tau with three variables alpha, I say if I have an instance of tau with variables replaced by some sigmas, which is smaller than tau prime, then tau prime is also of the form tau of something, for some variable sigma prime. This works for products. So in OCaml, if you have something which is bigger than a product, well, it's also a product. But it fails for filedest because filedest is smaller than int, and int is not of the form filedest. So this is the criterion that I must check for a GADT variance to be sound. So I have written a proof of that, but I won't show it in the slides. So, but now I have a problem, which is covariance means upward closure. To check contravariance, I must check downward closure. Downward closure is a symmetric property. If something is smaller than tau, then it is also of the form tau of something. But in OCaml, well, I claim that the product type was upward closed, but apparently no type is downward closed, because I can always define a private synonym, and I will get a type that is smaller and have a distinct structure. Does this mean that all my GADTs must be either invariant or covariant, and no contravariant allowed, or no arrow types? Well, so this is a problem of a closed wall vs open wall perception. Subtyping relation, sigma smaller than tau, is something I know about my type system. And the closure properties, they have the form, if a relation holds, then it is of this form, or said otherwise, no other kind of subtyping relation exists from this type. So this is a negative check. I must see what my subtyping relations are and check that none of the properties, none of them fail this test. And so it makes a closed world assumption. If I add new knowledge about I define new private types, I may break closure property. So there is one case when I can actually make this closed world assumption if I have a type that is defined inside the module and not exported. Otherwise, we claim that it is possible to resolve this tension between other closed world and open world by defining, when you define a new type, you say, okay, I want it to stay downward closed, so I will promise that I will never try to make a private synonym of it, and as a reward, you give me the right to use it as an instance of a contravariant GADT. So this is a suggestion of change to the Okado language that we considered, and we're still working on the details. So this is an interesting problem because there is a tension between restricting subtyping for the new type we define, and in exchange enriching the covariant properties of the GADTs we can define. It can be compared to the use of final classes in object-oriented language. When we define a class final, well, you abandon some freedom and then you gain some reasoning power on this class. Well, we propose to do the same kind of trade-off here, but we need more example to check if this is a correct choice and when do we decide to restrict the type in this way or not. So this is a high-level idea of the talk. And now I can give some more technical details because they were entertaining for me to develop, and I think they're not that interesting. So we must check if a given GADT definition is sound, or say no, your variant annotation is wrong. You should actually make your type invariant. Invariant is always correct. It's covariant or contravariant that may be wrong. And to do that, we need to check if a type is upward or downward closed. So I will try to not to be too long. So first I explain how I check variances with a judgment to check variance of variables which is close to what has been done before with a slight twist. It's useful for the rest of the development. It's not something extraordinary. And then I can extend this judgment to a judgment that checked upward or downward closure. And the idea is that I want a check in my type system which is easy to do for an implementation. So in the previous work we are relying on, work of François Potier and Vincent Simonet, there is a criterion which is given in semantic terms. If such constraint is satisfiable, then this is safe. But this is not something you can check easily in a type system, and we are specializing the criterion to get a pragmatic check. So first, variances. I suppose you are familiar with covariance, invariance, and contravariance. They form a lattice in the sense that invariance is more restrictive than covariance and contravariance. And they have obvious associated relations. So I have this preg of some variance, which is either smaller than, bigger than, and equal. And for completeness, I need to add a fourth variances, which was already present in some previous work by Andreas Adel, for example, which is irrelevance, meaning if a type variable does not occur at all in the type definition, well, it has a fourth, even more permissive variance, which I call irrelevance. And two types are in the irrelevant relation if true, meaning it's a full relation. And then if the variable alpha has variance v in alpha t, and beta has variance w in beta u, if I compose those two type expressions, what is the variance of alpha in alpha t u? I'm sorry for the hustlers in the room. I'm using the arguably not so readable OCaml syntax for types here, but you should be able to make sense of that. And this definition of what is a composed variance of alpha is this operation, v times w, which I define here. You can work out, it's quite easy. For example, if you have alpha is contravariant is t and beta is contravariant in u, well, minus times minus give plus, as you can see here. Okay. And then I define this judgment gamma tau v, meaning that, so in the context gamma, tau has variance v. Gamma is a context where each variable is annotated with a variance, and I'm checking that this variance annotation is wrong, is correct, in the sense that if the variables vary according to that variance, I have alpha and take alpha prime, which is bigger than alpha, for example, for a covariant variable. Well, the expression t will vary along v. For example, if alpha goes down, beta stays the same, and gamma goes up, well, this type expression will generally move to a higher type in the subtyping relation. And if both of my three variables stay equal, then I can claim that it goes to a higher type, but I can make the more precise claim that it stays equal. Usually when we check variance, we have judgments where there is no such v, and we change the context when going to a smaller type. So I have this type judgment here to see what's happening when I move to a subtype, so a parameter sigma of tau. I compose the variance v with the variance I, which is the variance associated to the ith argument of the type t. For example, in the arrow case, which is a special case of this rule, well, to check that sigma 1 to sigma 2 vary along to v, I need to check that sigma 1 varies along to v times minus, which is the symmetric negative variance of compared to. So closure properties, well, so I say that in our system alpha times beta is upward closed. This is a statement I make about the head type constructor times. And I say this constructor is upward closed. Some of them may be, some of them may not be. For example, object types are not upward closed because you can have a bigger type that is not the same object types. But if I have a richer type expression, I need to go down, recursively check subterms for upward closure or downward closure. And this is all about the structure of my type, the head type constructor that I find along the way. But what about variables? Here, all my examples have distinct variables. Well, if I have some multiple occurrence of a variable, well, it becomes a bit more complicated. For example, beta times beta is not closed, it's not upward closed. For example, if I have files times files, it is smaller than files type int, which is on the form alpha times beta, but not of the form beta times beta. So it's dangerous to repeat a variable twice. But in some cases, it's actually sound. So if my two occurrences are invariant, this is correct. Do the work in your head. If something is higher than beta ref times beta ref, it is actually equal to beta ref times beta ref. So we capture these subtleties through a zipping operation, v1 zip v2, which is partially defined. And so you may combine two occurrences of the same variable if their variants are such that this zipping operation is defined. For example, as you see, beta times beta, which is plus zip plus, is not defined in this schema, while invariant is defined. And with this stuff, baggage, formal technical stuff, I can define a judgment gamma v to v prime, which is an extension of gamma tau v. So I check that. So first, what I actually want to check is the upward closure property that I define that if I have an instance tau sigma of tau, which is smaller according to v than t prime, then t prime is equal to a tau sigma with for some sigma prime, small type of it. But to check that in an inductive way, I need to strengthen my hypothesis a bit, and I need to check for a finer property, which is if tau of sigma is smaller than tau prime, then I have some sigma prime, so that tau of sigma prime is not equal to tau prime, but is related by v prime. And when v prime is actually equal, I get the first judgment. So this two parameter judgment is my final gamma tau v to v prime judgment. So I'm running a bit out of time, so I will show you very quickly the inference rule. The important part here is that we check the variance in the important case, sigma t. Well, I have two action case. we check the variance of the head constructor T, which we check that it is V closed, and we use this zipping operation in context to check that the multiple occurrences are compatible or legal. And we check on the right side as we did for the previous judgment. And this is our definition of the upward closure or downward closure checking judgment, which allows us to check that the GADT definition is sound. Quickly, so there is another approach, which is, so what we did was to check if type equality is upward closed or downward closed. In fact, we could have another approach where instead of having type equalities in GADT, we would use subtyping constraints. So instead of saying alpha is equal to beta times gamma, I say alpha is bigger than beta times gamma. So this is a weaker property, which is obviously upward closed, because if I take a bigger alpha prime, well, alpha prime is bigger than alpha, then it is also bigger than beta times gamma, so it's closed by subtyping. And then, if I do this new definition in a hypothetic language which supports this kind of GADTs, well, I can do pattern matching as before, but I only get a subtyping hypothesis instead of a type equality in my context. So some functions will still be typable, like this one, evil is still typable, but some functions which rely on both directions of the equality will not be typable anymore. The question is, are there interesting such functions? We must see. But this is less convenient. Why? Because the use of subtyping here must be annotated explicitly, while the use of the local equations was implicit with unification. So if we choose to go this path, we have a weaker type, and it's less convenient to use, which is why we did the hard work of checking upward closure, downward closure, and thinking about the language design issues. Okay, so I'll skip that slide. To conclude, GADT variance checking is surprisingly less obvious than we initially thought. It's not anecdotal. I'm not so. GADTs are an important feature, but it's not a defining feature of your type system. Subtyping has pros and cons, let's say this way, but still this work raises interesting design questions on, so this negative property of if I allow more stuff in my type system, well, I will actually be more restricting in the end, so I must give the programmer the tools to say, here, locally restrict my subtyping relation because I want more freedom later. I think this is an interesting design question that we should consider for language design. And finally, we have the sound criterion. I have a technical report in progress with the full proofs of correctness that can be implemented easily using an algorithm version derived from my inference rule shown before in a type checker, for example, a OCaml type checker. Okay, so just an advertisement before having questions. Check our blog. We have a blog where we blog about our research, which is a good idea, and more people should do that. Thank you.